All right, today we are going way, way beyond your car's GPS. We're going to talk about the algorithms that power some seriously complex networks, the ones that have to figure out the absolute best path when the real world starts throwing curveballs. Think fees, discounts, or even needing to know every single possible route all at once. To do that, we have to start thinking in terms of graphs. A bunch of points connected by lines.
Right, so your GPS is pretty straightforward. It finds the shortest path between cities using roads. But what happens when shortest isn't so simple? How do networks find the best path when some of those connections have penalties? Or, and this is where it gets really wild, what if you could use them to spot a money-making opportunity in currency markets? Okay, here's how we're going to break it all down. We'll kick things off with the classic positive path problem and the famous algorithm that solves it. Then we'll look at how to make that algorithm run crazy fast. After that, we'll throw a wrench in the works with penalties, or negative paths, and see how to spot these really interesting cycles. And finally, we'll tackle the big one, how to find all the shortest paths at the same time. So, first up, the foundational scenario. We're trying to find the shortest path in a network where every connection, every edge, has a positive cost, like distance or time. This is the perfect job for a brilliant and, kind of famous algorithm from a guy named dijkstra.
The specific problem we're solving is called the single source shortest path problem. It's pretty intuitive, actually. Just imagine you're standing at a central warehouse, and you need to figure out the absolute cheapest or fastest way to get to every other city in your delivery network. That's exactly what we're trying to solve here. So how does Dijkstra's algorithm actually do it? Well, it's what we call a greedy algorithm, and it's super clever. It starts out by assuming every destination is infinitely far away. Then, in each step, it just picks the closest unvisited point and checks with its neighbors, basically asking, hey, is it shorter to get you guys through me? It locks in the closest path first, and then the next closest, and so on. This works perfectly, as long as there are no negative weights to mess things up.
Okay, but that one step, select the unvisited vertex with the smallest known distance, that sounds like it could be a real drag. I mean, if you've got a graph with millions of nodes, having to scan through all of them to find the minimum every single time, that's got to be a huge bottleneck, right?
Oh, it absolutely would be. But that's where a really cool data structure comes into play, the priority queue. You can think of it like a super organized, self-sorting to-do list. It's built to do three things really, really well. Add new items, instantly pull out the highest priority item, which for us is the vertex with the minimum distance, and quickly update the priority of anything else on the list. It's basically custom built for what Dijkstra's needs to do. And what's so important to understand is that the kind of priority queue you use has a massive impact on performance. Sure, a simple array works fine for small or really dense graphs, but for sparse networks like a road system or the internet, using something called a binary heap gives you a huge speed boost. And for absolutely massive graphs, a Fibonacci heap gives you the best performance, at least in theory. The choice of data structure here is just as important as the algorithm itself. Okay, so Dijkstra's is our go-to for positive paths. It's fast, it's efficient, but what happens when a path can have a penalty, a fee, or even a discount? In graph language, what happens when we let negative edge weights into the party? Well, this is exactly where that greedy approach completely falls apart. Yep, this is the problem. Dijkstra's algorithm is so eager. It locks in a path as soon as it picks the closest vertex. But imagine it does that, and then later on, it discovers a path with a big negative edge. That negative edge could have created a massive shortcut to a vertex that Dijkstra's already marked as done. Its greedy choice turned out to be short-sighted. It basically gets tricked.
So clearly, we need a new strategy. We need an algorithm that's more patient, more methodical, one that doesn't commit too early. Instead of just grabbing the closest thing it sees, it needs to be able to reevaluate every single connection in the graph, again and again, until the true shortest paths finally bubble to the surface.
And that brings us to the Bellman-Ford algorithm. Its strategy is beautifully simple, but incredibly powerful. It just iterates through every single edge in the whole graph and checks if any path can be improved. And it does this over and over again. Specifically, it does it n-1 times. This repetition guarantees it finds the correct shortest path, even with those tricky negative weights, because the longest possible simple path can't have more than n-1 edges. Now, letting negative weights in the door introduces this really fascinating and sometimes profitable side effect, the negative weight cycle.
And this isn't just some abstract idea. It can represent a very real thing, like an arbitrage opportunity in financial markets.
So check this out. Imagine this chain of currency trades. You start with $1. You convert it to euros, then those euros to Japanese yen, then the yen to Russian rubles, and then, finally, you convert the rubles back into US dollars. But look, after all those hops, you end up with $1.03. You actually made money just by moving it around in a circle. You found a profitable loop.
So, how does a profitable loop like that translate to a negative weight cycle? Well, there's a neat math trick involved. If you take the negative logarithm of all the exchange rates, that profitable loop, where you're multiplying numbers to get a result greater than 1, magically transforms into a path whose edge weights add up to a negative number.
So you've basically got an algorithm that can detect a free lunch. The big question is, how can a piece of code systematically sniff out these opportunities? All of a sudden, this shortest path problem becomes a tool for finding guaranteed profit.
And this is where the Bellman-Ford algorithm is just so elegant. After it's done its required n-1 passes, it does one more bonus round. It relaxes every edge just one last time. And if the cost of any path in the graph still gets shorter on that extra pass, that's the smoking gun. It's definitive proof that there's a negative weight cycle, a loop so profitable you could just keep running through it, lowering your cost forever.
So far, everything we've talked about, dijkstras and Bellman-Ford, they've been focused on finding paths from one single starting point. But what if you need the whole picture? What if you need to know the shortest path between every possible pair of points in the entire network?
Well, that's what we call the all pairs shortest path problem. Now, the obvious solution might be to just run Bellman-Ford from every single starting vertex, one by one. But that would be incredibly slow, especially on dense graphs where there are tons of edges. We need a smarter, more holistic approach.
And for that, we turn to the Floyd-Warshall algorithm. It uses a method called dynamic programming. We start by building a matrix that only shows the direct paths, the paths with 0 intermediate stops. For instance, the direct path from vertex 4 to vertex 1 has a cost of 2. But there's no direct edge from 4 to 2, so for now, we say its cost is infinity. Okay, now watch this. This is the magic. In the very first step, the algorithm asks a simple question. Can we find a shorter path between any 2 points if we allow ourselves to go through vertex 1? Now look at the path from vertex 4 to 2. It was infinity, but we know the path from 4 to 1 is 2, and the path from 1 to 2 is 3. So the total path, 4, then 1, then 2, has a weight of 5. That's better than infinity, so we update the matrix. The algorithm just keeps doing this for every single vertex, systematically building up all the optimal paths at once. So, to bring it all home, here's the tale of the tape. Dijkstra's is your specialist. It's super fast, but only for problems with positive weights. Bellman-Ford is your robust, methodical workhorse that can handle negative weights and even detect those crazy cycles. And Floyd-Warshall is the powerhouse, the one that solves the entire all-pairs problem in one go. Each one is the right tool for a very specific job. And that really brings us to the final thought here. These incredible algorithms do so much more than just route internet data or find your driving directions. They're at work under the surface, determining financial opportunities, planning global logistics, even analyzing complex biological networks. So, where else in your world are these complex pathfinding decisions being made for you, completely unseen?
Hey, if you enjoyed this deep dive into graph theory, do us a favor and like, share, and subscribe for more explainers on complex topics like this one. Thanks for watching.